Okay, this is the P3 paper from June 2023. It's question number 7, and as we can see by looking at this, it's an exponentials and logarithms question, in particular exponential modelling. And then when we get on to part B, we've got to find the rate of decrease of bacteria, which will be dn by dt when we get down there. So we'll be differentiating exponentials at that point as well. But let's look at the question. So it says, scientists are studying 2 different populations of bacteria. So we've got 2 different functions. We've got this for part A and then this one for part B. Well, we're looking at part A. So if we're looking at part A, n is AE to the KT. And it tells me in the bullet points, at the start of the study, the population is 2,500. So that's t equals 0, n equals 2,500. And then secondly, it tells me when t equals 8, n is going to be equal to 10,000, and it asks us to find the exact value of A and then the value of K to 4 significant figures. So just be aware of that when we're going through and doing the question. Let's make a start to it. So part A, it says n is equal to AE to the KT, and it says initially, so when t is equal to 0, we know n is equal to 2,500. So 2,500 equals AE, but t is equal to 0, so we don't need to worry about the k. We just get AE to the 0 there. E to the 0 is 1, so that does give me A being 2,500. So there's the first bit done. And then it also told me that at t equals 8, n was this time equal to 10,000. But we know that A is equal to 2,500. That's a constant, so that can be put into my function now. So we're going to get, if we substitute everything in, 10,000 is equal to 2,500 for the A, E to the KT, so that's going to be E to the 8K, and we can solve for that. Divide both sides by 2,500. We get 4 is equal to E to the 8K. So log both sides, log 4 is going to be 8k, and then we want k obviously, so k is 1/8 log 4, but if you read back, it said that it wanted k to 4 significant figures. Unusual. I'm surprised they didn't just leave it as an exact value there, but k is equal to 0.1733, so that's the first part done. Part B, it says the number of bacteria in the second one is this second function here. Find the rate of decrease of bacteria in this population exactly 5 hours from the start. So rate of decrease of bacteria, bit that I spotted right at the start of the question, that's going to be dn by dt. And then we want it when t equals 5, and we want it to 3 significant figures when we get that far. Let's do it though. So part B, we had that n was equal to 60,000 e to the minus 0.6 t. So dn by dt, that looks horrible, but it's not particularly difficult to differentiate this, hopefully for you. If you differentiate e to the 2x, you get 2e to the 2x. What we get is that part there, that's the multiplier. So I'm going to get minus 0.6 multiplied by 60,000 e to the minus 0.6t. If that's causing you problems, you're going to need to go back and do some more work on that, I'm afraid. That is a relatively straightforward. These functions always look like this. They always look like something horrible when we're doing the exponential modelling, but actually working with them isn't too bad. And we wanted dn by dt when t equals 5. So at t equals 5, dn by dt is equal to, do you know what I would do though, first of all, is just actually work that bit out. That's minus 36,000 e to the minus 0.6t. And now at t equals 5, then that's minus 36,000 e to the, putting t equals 5 in there, 5 times minus 0.6 is minus 3. I'm used to giving exact value answers, but they don't in this case. This works out to be minus 1792.33. But they actually said, no, can we have that to three significant figures, if we go back and check the question. So, yep, we've done part B. And then part C says, right, at T equals capital T here, the number of bacteria in the two different populations was the same. Find the value of T, giving your answer to three significant figures. Okay, so what we've got to do is basically we've got this function and we've got this function, and what we need to do is sub T equals capital T into both of them and then equate them. So let's actually tell the examiner what I'm doing. So at T equals T, 60,000 e to the minus 0.6 T, that's putting T equals T into the second formula, is going to be, not A e to the KT, we've got our values here, is going to be 2,500, that's A, e to the, and use the values that they've got, that we had 0.1733 as our K up there, and now, I've just got to solve that equation there. So if I've got to solve that equation there, let's divide everything by 2,500 first. So I'm going to get 24e to the minus 0.6t is going to be equal to e to the 0.1733t. Now you can do this quicker than that. I was just doing it in step by step here. If I now divide by that, and again, I'll do it, but I wouldn't do this if it was my own work. I get 0.1733t divided by, so we're dividing by a minus. Yeah, it might be worth just doing this just to make sure that we don't make any mistakes here. Okay, so when I divide that down, now what you can do using your indices rules is just to add the power, so it's to subtract the powers. 0.1733t minus 0.6 is going to give us e to the 0.1733 plus 0.6 t there. Okay, just fussy when we're doing all this, but if I get to that stage, then log both sides. Log 24 is now equal to whatever 0.1733 plus 0.6 is. So that's going to be 0.7733 t, and so t is going to work out to be log 24 divided by that, which gives me apparently 4.1097, and then go back and just check. I think it said, let's have a look, to three significant figures there. So a little bit fussy with all that working out, and they're trying to catch people out who are not confident and people who are not really careful. That's a nasty little bit just in there to make sure that we get that right. But 3 marks for that, and yeah, quite an interesting question. Hopefully that will make sense to you.